Second day of chapter 2. We've done all this crazy stuff with these derivatives, and problems have gotten pretty cumbersome. We haven't done very many of them. We need to make this a lot more efficient. So how are we going to do this? Instead of using alternative form or definition of the derivative, we are going to differentiate these functions now using what we call the power rule. Well, how does the power rule work? Now, again, please remember that the derivative is defined as the rate of change of a function at a specific x value. The rate of change of a function at a specific x value. So we get into the slope of the tangent line. We get into all kinds of these different things. So when we start with these now, we're going to try to look at them from a shortcut perspective rather than looking at them from all this theory that we've been doing. So this first one, all right, so I'm going to find the derivative. Now get used to the fact that dy over dx, I'm taking the derivative of y with respect to x. So what is dy over dx? Well, what's the derivative of 3? Well, 3 is a constant. 3 is a constant. By definition, a constant doesn't change. So what is the rate of change of this function? The rate of change of this function would be 0. So a little note for everybody. The rate of change, the derivative of a constant is always 0. Second one, what's my derivative? Well, my derivative, this time I'm taking the derivative of f of x, so we like to use f prime of x. It kind of follows along with the format the problem was presented in. So now here's what you do. Instead of doing alternative or definition of, I guess we'd have to use definition of because we don't have an x value given to us. Take the power, multiply by it, take x, raise it to 1 less power. Done. It's a wonderful, wonderful thing. So what exactly just happened right there? Every derivative, every term in a problem will have its own derivative. And the fastest way will be, if it's a simple x raised to a power, you're going to multiply by that power and subtract 1 from that power to get the new power that is on x. So what do we mean by that? So if we look at this number 3, first thing I want to notice, well, there is a single term here. So let's rewrite this single term. If I rewrite it, that's going to be x to the 2/3 power. And then, well, let's see. So now when I go to take my derivative, it's a single term, single derivative. Put the new power down in front to multiply by it. Take that x and raise it to 1 less power. So 2/3 minus 1, or minus 3/3, would be negative 1/3. And you know you can't leave a negative exponent in a problem, so since you can't leave a negative exponent in the problem, how about we call this 2 over 3x to the 1/3. That would be a wonderfully acceptable answer. Or if you're not a fan of fractional exponents, 2 over 3 times the cubed root of x, or cubed root of, how about if we make it cubed root of x here instead of cubed root of 3. So either one of those would be just fine. Now what I want you to do is I want you to look at this problem number 3 critically so that you can see I made a pretty good sized mistake right here, because you'll notice I just have a string of equal signs. And so that assumption is, that, what a lot of people like to do is we like to just equal, 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 equal. You're trying to find the derivative. And so what some people will do is they'll say, Mr. Perkins, you're just being difficult about this. You're being difficult. So fine, whatever. I took the derivative right here. But now, if you look critically, because their assumption is, well, in the first step, you take the derivative and then you simplify. Well, if you look at what we just did with problem number 3, we didn't take the derivative in the first step. We rewrote the original problem. So if you wrote what I have in green right there, you actually made 2 mistakes. This is not the derivative. This is not the derivative. It's gone. The derivative happened when we took that x to the 2/3 and we changed it. How did we change it? We differentiated it, or we took the derivative of it. So there's where you're going to put your label. And that's something that you need to get in that habit of right now. Okay, number 4. Here's what a lot of people are going to try to do. A lot of people are going to try to take this problem, and they're going to take the derivative of 1. They're going to go 1's a constant, so put a 0 on the top, and x cubed, 3x squared on the bottom. This is wrong. Don't do it that way. Okay, what's wrong with it? Well, if you did what I have in blue, you're assuming that there's 2 terms there. That 1 is its own term and x cubed is its own term. That's not true. There is a single term here, and that single term is really x to the negative 3rd power. And now when you go to take your derivative, new power, or multiply by negative 3, subtract 1 from negative 3, which means it's going to become negative 4, and clean it up. How about negative 3 over x to the 4th? So, again, we can do a whole lot of these problems in the same amount of time that it took us to do one problem before. So let's look at number 5. So number 5, again, here's what people are going to try to do. People are going to go, oh, I see this x to the 2/3. It's on the bottom, so better give it a negative exponent. So people will try to say that this is the same thing as 3x to the negative 2/3. But it's not. That 3 doesn't have anything to do. If you move that 3 to the top, it's got to have its own negative exponent. So those are absolutely not true. So we're going to want, again, to get this thing totally out of the problem because it's not true. So what we'll do is we'll rewrite this problem. We'll rewrite it. That 1/3 can stay as it is. So what we really have is we have 1/3 times x to the negative 2/3 power. The x, the 2/3 for the same reason that it was 2/3 in problem number 3. It's on the bottom, so we're going to give it a negative exponent, move it up, and then that 1/3 has its own power. It's independent of the x itself. So we're going to leave it where it's at. So now when I go to take my derivative, well, the 1/3 is a constant, so let's bring that along for the ride. And now we're going to multiply that by the derivative of x to the negative 2/3. Well, we already did this once, so that's going to be, bring the new power down, so multiply by negative 2/3 and subtract 1 from the power. But now if I'm subtracting from negative 2/3, take 3 more thirds away from 2/3, we're going to have negative 5/3. And now if we want to clean all this up, we'll take the 1/3 and the negative 2/3 and multiply them together. Well, 1/3 times negative 2/3 is negative 2/9. So negative 2 on the top, 9 on the bottom, and let's move the x to 5/3 down to the bottom and give it its positive exponent. And sure, you could put a radical in there if you wanted, but I don't think it's really necessary. Number 6, you'll notice count terms. We've got 1, 2, 3 terms. If we've got 3 terms, then we're going to take 3 derivatives. So the first derivative, well, there's the constant negative 1/2 multiplied by x to the 4th. So that would mean we're going to take negative 1/2 and bring it along for the ride and multiply it by the derivative of x to the 4th, which would be 4x to the 3rd. And then we've got a plus 3, and we're going to multiply that by the derivative of x cubed, which would be 3x squared. And then we've got a minus 2, and we're going to multiply that by the derivative of x. Well, the derivative of x, let's see. So that would be a 1x to the 0. So what you have with constants in terms is they really are just kind of coming along for the ride. And now when you clean it up, negative 1/2 times 4 is going to be negative 2x cubed. 3 times 3 is going to be 9x squared. And this last term, because it was x to the 1st and we subtracted 1 from the power, there's not going to be an x in that last term, or it's to the 0 power. So there's a pretty good look at shortcuts. This last question, I want to kind of apply the shortcut a little bit, or this number 7. Problem number 7, find the equation of the tangent line. Well, equation of a line. Let's think back to algebra. Equation of a line, I need a point and a slope. So y minus whatever the y-coordinate is times m, which would be my slope, times x minus whatever the x-coordinate is. Okay, well, they're telling us to do this at x equals negative 2, so let's put the negative 2 in. How do I find the y-coordinate? I would do f of negative 2. Well, f of negative 2, 5 times 4 is 20, minus 3 times negative 2 would be positive 6. So we got 26 plus 2 is 28. So 28 is my y-coordinate that I'm using. Now I need to come up with a slope. So when I go to come up with my slope, so now slope has to do with your derivative. So let's find our derivative. Again, without the alternative form of the definition of the derivative, it'll save us a lot of time. So 5x squared, get rid of that intermediate step that I wrote in problem number 6 up there. So 5 times 2x to the 1st would be 10x to the 1st, minus 3x to the 0, plus the derivative of 2 is going to be a 0. So there's my derivative. Why did we do the derivative? We did the derivative so that we could, so that we could plug in a specific x value, in this case, negative 2, and come up with a slope. So 10 times negative 2 is negative 20 minus 3. My slope of my tangent line is going to be negative 23. And this would be a perfectly acceptable answer for an AP person. in order to save time. You've got all your values. If you wanted to clean it up, let's see, so we distribute negative 23. So how about if we distribute negative 23, so negative 23x, we're really adding 2 with that double negative times negative 23 would be minus 46, and then we're going to be adding 28 to it by moving it to the other side. So how about y is equal to negative 23x minus an 18, and that would be another excellent way to write that solution. So there's your shortcuts for finding derivatives, and a quick using a shortcut to find the equation of a tangent line, which is ultimately what we're going to try to do with a lot of these things.